Welcome back. More on the paired design. I'm looking at Thomason 1 again, the same 12 students with their pre-tests and post-tests, and the nice short confidence interval on the effect size. That's the average gain score from pre-test to post-test. Next step is to consider Cohen's D, the standardized version of this effect size. So I click down at red 9 and there's the panel for Cohen's D. As you know, Cohen's D is an effect size divided by a standardizer. The effect size we want is MDiff, the mean of the different scores, about 1.67 here. And the standardizer we want is, well, our best estimate of the population standard deviation for LSAT scores. And we could estimate that population standard deviation with our pre-test standard deviation or our post-test standard deviation. In fact, we use an average of the two down here as SAV, and there's the formula there in this pop-out. So Cohen's D will be our effect size divided by our standardizer, 1.67 divided by 3.1, that's D of 0.535 here. Our standardizer, 3.1, well, compare it with the pre-test standard deviation, about 3.3, post-test about 2.9, so 3.1 makes sense. We've got 11 degrees of freedom, quite small, so D unbiased is noticeably less than D, around 0.535, D unbiased 0.498. Next step, we'd like the confidence interval. That's our interval estimate for Cohen's delta. That's the standardized effect size in the population. And Esky needs to do a bit of complicated calculation there. Watch right now, and I'll press this button and you'll see the values pop up here. There we go. The confidence interval for delta is from 0.18 to 0.88. So we can say our best point estimate is close enough to 0.5, with a confidence interval from 0.18 to 0.88. If you're interested in p-values, we can look at how this confidence interval compares with 0, a long way away, a very small p-value, and there it is, 0.003. Do we need a separate p-value for Cohen's D? Well, not really, because testing whether this effect size in original units is 0 is pretty much the same as testing whether our standardized effect size is 0. And so we'll get pretty much the same p-value whether we do the calculations in original units or in standardized units. 0.003, really quite strong evidence that there is some non-zero effect in the population. But as usual, the confidence interval is much more informative. It tells us, yes, there's strong evidence against 0, but still there's a fair degree of uncertainty there in the extent of that interval. Our best point estimate about 0.5, and a confidence interval running roughly from 0.2 to 0.9, so really quite a lot of uncertainty there in our population estimate. Why did we use SAV again? Because we wanted, as our standardizer, the best estimate we have of the standard deviation in the population. Why did we need SDiff here, something that's typically smaller, not guaranteed, but usually smaller? Because that's what we need to calculate this short confidence interval on our effect size. So be quite clear about the different roles of these two different estimates of standard deviation. Standard deviation of the differences for calculating our confidence interval on the effect size, the differences, and SAV, our best estimate of the population standard deviation that we use as our standardizer for Cohen's D. Next, let's go to the next page in Esky, Summary Paired. There it is. And here I've got the data for actually Thomason 2. And here I only need to put in summary statistics, not the full data. So if you only have summary statistics, use this page for the paired design. I enter sample size 16, mean and standard deviation for pre-test and post-test, and I have to enter one more thing. SDiff, the standard deviation of the differences, 2.1 there. Why do we need this? Because that's the critical piece of information we need to calculate the confidence interval on our effect size there. This line joining the means, yes, that signals we have a paired design. Cohen's D, once again, I'll click down here. D will be calculated as our original unit's effect size, 1.37 MDiff, divided by SAV, that's the average of the two standard deviations, which are 3.4 for pre-test, 4.3 for post-test, so about 3.9 makes sense. D is this 0.354, and again, when I unbias it, 0.336. Now, let's calculate the confidence interval for Cohen's delta, the standardized effect size in the population. Press the button, and off it goes, and there it is. If you read these pop-outs, you'll see there are some limitations on the situations in which ESCI can calculate a confidence interval for delta, but only rarely does that make much difference in practice. So here's our point estimate, 0.34 D unbiased, and the confidence interval on that from 0.05 to 0.65, a very wide confidence interval reflecting this really quite long confidence interval on the original unit's effect size there. If you want a p-value, you could say, well, here we have a little bit of evidence. P would be less than 0.05, in fact 0.021, and again that applies for original units and also for Cohen's D. We've got enormous overlap between these two confidence intervals for pre-test and post-test. Do we care? Does that matter? Remember, with the independent groups, we look carefully at overlap of our two independent confidence intervals, and when they overlapped very greatly as they do here, that meant no evidence at all of a population difference between these two means. But for the paired design, the situation is extremely different. For the paired design, signaled by this line, we hope that the confidence interval on the effect size, on the differences, will be quite short. And if it is, despite having big overlap here, we might have a bit of evidence that we've got a true difference in the population. Can we have an overlap rule for the paired design? Absolutely not. The extent of overlap or non-overlap of these two confidence intervals is virtually irrelevant for what we are really interested in, which is the effect size and the confidence interval on the effect size. Very often, this confidence interval is smaller than either of these, but it doesn't have to be. It's only much smaller when we have strong positive correlation between pre-test and post-test results. It's even possible for this confidence interval to be longer than these two if we don't have such a correlation. It doesn't happen much in practice, but it's possible. Bottom line, for the paired design, we have to know the information necessary, standard deviation differences, to calculate this confidence interval. If we're only given these two means and confidence intervals in a figure, we cannot interpret. There is no possibility of an overlap rule for the paired design because this figure of just these means and confidence intervals does not have the information we need to do statistical inference and draw a conclusion about what we're interested in, which is this difference. We need additional information so we can get this confidence interval on the effect size we're interested in. So let's consider independent groups and paired. Which should you use? Well, it depends. Here we are back at data 2, seeing the data for the first pen laptop study, 2 independent groups. Independent groups is really the simplest design. Each participant is tested under just one of the levels of the independent variable, and because the pen and the laptop data come from independent groups, these two sets of data are fully independent. Now, sometimes you have to use independent groups. If you're comparing male and female or left-handers and right-handers, you need independent groups. In other situations, pre-test, post-test, you must use paired. But often, as with pen and laptop, you have a choice. So you could take a single group of students and test them on one day with pen and on another day with laptop. The danger, though, is carryover effects. Perhaps their experience with pen would lead them to do better or to be more fatigued or in some other way change their performance with laptop. A good strategy to minimise that sort of carryover effect is to counterbalance the order of presentation. So half the students would take pen on one day and laptop on a later day, and the other half would take laptop first and then pen. At summary paired for the pre-post design, the paired design signalled by this line between the means, how could we minimise the carryover, perhaps the learning effect of doing the pre-test on the post-test? Well, one way to attempt to do that is to have parallel forms of the tests. And that's what Thomason and colleagues did for the critical thinking studies. They had, for example, two versions of the LSAT, versions A and B, parallel forms, designed to be of similar difficulty and tap the same abilities, critical thinking, but to use different questions. And so some students would do Form A at pretest and Form B at post-test, and other students B at pretest, A at post-test, hoping that any carryover effect would be minimised by using these parallel forms. As usual, deciding between these two designs is a matter of your informed judgment in the research context. I very often much prefer to use a paired design if it's applicable, if I can find ways to reduce any carryover effects. If testing is cheap and participants are numerous, then perhaps independent groups is simple and straightforward. But if we have few participants available, and if testing is expensive and difficult, well then we should try quite hard to see whether we can find a paired design that is practical. Yes, build up your confidence in your judgment and choose. And if you go for a paired design, quite likely you'll get a nice, precise estimate of your effect size, which is terrific.